This is team HEC 28. The title of our project is to design an integrated protein exchange membrane fuel cell system. Next. My name is Daniel Jordan.
Oscar Palencia.
Marco Ponce.
Rawan Rizal.
The purpose of this project is to model and simulate the balance of plant for a regenerative fuel cell system that can serve as a backup energy source in lunar environment. Next. NASA has continuously looked for ways to develop an effective power generation system that can provide sustainable energy to meet its challenging environmental conditions in lunar space. One device that NASA has implemented is the fuel cell. Unlike batteries, which runs out over usage, fuel cell produces clean, hazardous-free, constant power. It produces electricity through an electrochemical process between hydrogen fuel and oxygen to produce water and heat as a byproduct. Theoretically, the efficiency of the fuel cell is 83%, while the power needed for one lunar cycle is 100 watts. The design is a self-contained unit that can be transported to the lunar space, where it can be powered on by a photovoltaic cell during lunar day. Since the project is meant for lunar exploration, our design was modeled under Earth-based conditions. By doing this, we were able to replicate the design by using simulation to show performance of the whole system through the in-lab testing of the anode side to generate a power of 100 watts. Next. This animation shows how hydrogen flows into the fuel cell through the anode side and oxygen through the cathode side. The hydrogen ions flows across the membrane towards the cathode, while the electron flows through an external cycle, does work, and returns back into the fuel cell. The oxygen from the cathode recombines with the incoming electron and hydrogen ion to produce water and heat as a byproduct. Next. It is regenerative because the electricity produced using water from the fuel cell to produce oxygen and hydrogen by way of the electrolyzer, which is then recycled back into the fuel cell for continuous flow of power. Next.
Here is our project objectives. Last semester, we focused on design, which is to create the balance of plant for the fuel cell system. This semester, we focus on the simulation and testing. Simulation in the operation of the balance of plant as to see the relationship between various components. And the testing as to build and test an anode side using Earth-based conditions as to give a physical representation of the system. And the last objective is the power, to deliver a net power within 100 watts as the value was set forth as a requirement for the project. Here we have the specification table. The simulation models were using the fuel cell and the electrolyzer from these two brands, which is Infinity and Sustainable Innovations. For the fuel cell, it had a number of cells of 7 with an active area of 150 centimeters square. For the electrolyzer, the number of cells was 5 with an active area of 80 centimeters square. Simulation enables experimentation on a valid digital representation of a system. The simulation are key to see if the values are reasonable and acceptable for the project.
This is our Simulink design schematic. At number 1 is a PEM fuel cell, which will convert the chemical energy of hydrogen and oxygen into electricity through chemical reaction. Number 2 shows the electrolyzer, which breaks down water into hydrogen and oxygen. Number 3 shows the hydrogen and oxygen entering the fuel cell through the anode side and cathode sides respectively. And the number 4 is a water storage tank, which holds the fuel cell byproduct, which is water. And for the thermal fluid management, we have a cooling line, which will use DI water, heat exchangers, and dehumidifiers. And there's also supporting components such as pumps and compressors. The Simulink modeling and simulation the team conducted will focus mainly on the fuel cell, electrolyzer, storage tanks, pumps, and compressors. Next.
Our model was based on a 24-hour cycle with the fuel cell operating for the first 12 hours. A small time sample is simulated to show the zero initial condition, transient, and steady state of the fuel cell. The fuel cell subsystem was modeled with the current being the input and the mass flow rates of the gases and water being the outputs. Next. For the last 12 hours of the 24-hour cycle, the electrolyzer is in use. The small time sample shows the dynamic behavior of the electrolyzer from its zero initial condition, transient, and steady state. Much like the fuel cell, the electrolyzer was also modeled using the current as the input and the mass flow rates of the water and gases being the output. However, since the fuel cell consisted of 7 cells and the electrolyzer of 5 cells, the electrolyzer had to be adjusted to match the mass flow rates of the fuel cell, which we use for our BOP components. Next. The H2 and O2 storage tanks were simulated for a complete 24 hours. They were modeled using the ideal gas law. For the first 12 hours, the pressure and moles of the gases are depleting. This is due to the fuel cell using the gas as fuel in the chemical reaction that produces a power output. For the last 12 hours, the pressure and moles of the gases are increasing. This is because the electrolyzer is in use. This time period is also known as the recharging phase. Next. For the water storage tank dynamics, the opposite behavior is observed in comparison to the gas tanks. A positive slope is observed for the first 12 hours because the water is being produced as product of the chemical reaction taking place in the fuel cell. The electrolyzer then uses the water for the last 12 hours to break down hydrogen and oxygen back into its gas states. Next. The results show that both temperature and pressure influence the fuel cell's efficiency, which also affected the round-trip efficiency of the RFC system. 3 cases were simulated where only the fuel cell's operating conditions differentiated and the data recorded. Next. For the 3 cases, the temperatures were changed and the pressure ratios were also changed, which yielded 3 different round-trip efficiencies. The fuel cell generated 174 watts. The pump consumed 0.02 watts. The compressors consumed 13 watts. And the electrolyzer consumed 378 watts, which was provided by the solar panels. In terms of power in and power out, the power efficiency was 44%.
Here we have the in-lab testing. As mentioned before, the testing was using Earth-based conditions. The setup was evolving due to improvements throughout the semester. The complexity also grew due to add-ons done to the system. The arrangement of the components was important to easily locate errors, but as well as to keep everything compact to minimize space.
The figure shows the layout of the lab setup of the equipment to run the fuel cell in the earth-based condition. The system starts from the hydrogen generator, which supplies hydrogen to the fuel cell, produced from the electrolysis of the distilled water. The hydrogen is then passed to the mass flow controller, where we control the flow rate, and to the pressure transmitter, which controls the pressure. After that, hydrogen goes to the fuel cell through the supply valve. The blower attached to the fuel cell will provide the oxygen and also cool the fuel cell. The water and the excess hydrogen are forced out through the pores valve. The voltage and the current from the reaction in the fuel cell is measured using DC electronic load device. Next. The fuel cell tested in the lab was S100 by Horizon brand with 20 cells and power output of 100 watts. The operating temperature for this fuel cell was around 25 degrees centigrade and the pressure between 21 to 22 psi. The hydrogen generator was QL1000 by Fuel Cell Store, which produced 99% pure hydrogen at the flow rate between 0 to 1 liter per minute and the pressure between 30 to 60 psi. The AC voltage of 110 to 220 volts was supplied to run this generator. Next. Figure shows the electrical diagram of the tested system. Arduino microcontroller was used to control the blower and the valves, whereas NI USB data acquisition device was used to measure and record the flow rate, pressure, and the temperature of the hydrogen supplied to the fuel cell. Next. Data was collected and recorded using the LabVIEW. Figure shows the front panel of the testing, which includes the control for the blower and valves and the measurement for the temperature, pressure, flow rate, voltage, current, and the power. Next. Here is the videos which shows the quick demo of the experiment. The generator is producing hydrogen at the given flow rate, which passes through the flow meter that will adjust the flow and pressure going to the fuel cell. The output voltage and the current from this fuel cell will be measured using NIDC electronic load and in the LabVIEW front panel. The factors that affected the testing results were pressure, flow rate, temperature, and the time of the operation. The optimal performance was obtained at 8 psig and 1.023 standard liter per minute and 23 degrees centigrade, which was around 80 watts, operating at 14.5 volts and 5.5 amps. Next.
One of the feature improvements that the team had was to maintain steady flow rate. The optimal performance was rated at 1.4 standard liters per minute. However, the flow rate was capped at 1 SLPM by the flow meter specifications. Next. In conclusion, theoretical analysis and calculations were performed to confirm the effectiveness of the design. Simulink was used to model and simulate the BOP under lunar conditions. Then, anode-side testing was conducted using Earth-based conditions. This is important because to see how the similar system to our design schematic would do in a real-world scenario. The pressure and flow rate had the greatest influence on both the simulated and in-lab testing results. By completing this project, the team could understand the importance of a balance of plant and how it affects the efficiency of a system. Next. The team would like to acknowledge the following UT Tyler faculty members, former team member, and finally TSGC, who are project collaborators and sponsors. Thank you for watching our Design Challenge Showcase, and we'd like to open the next few minutes for questions.